Hi. Thanks for having me. For my for brief introduction of myself, I founded zero knowledge research community called CK Seoul in 2019, and then the project's radius actually came from this community. We were looking for real problems to be solved with cryptography, like encryption and ZK, and then MEV was one of them 2 years ago. So since then, we've been implementing some kind of delay encryption and our own ZK scheme called PVDE, and then now we are trying to solve big problems such as interoperability between multiple rollups. So today, our presentation is about the composability for rollups. So before going deep into the topic, I'd like to introduce that some thesis that I've drafted a month ago called Modular towards Microservice. Moving from monolithic architecture to modular is not like uncommon. It's kind of existing from traditional IT infrastructure such as AWS cloud. So to get better performance, AWS adopted this modular architecture to support multiple services with their clouds. So you can see on the right that there are many modules, and then AWS split the monolithic functions into specific functions, such as like data storage module and gateway to support many transactions from user side, and then and then something like storage, so they can store massive amount of data in efficient way. So and then they moved from modular to microservice architecture to support more to get more performance, more scalability, and also cost effectiveness as well. How to do that? They split with more into more many modules, and then this led to more optimization into each modules. So, but the problem is complexity is increasing. So they decided to adopt some kind of orchestration module to coordinate these all modules, so they can get better performance and somehow cost effectiveness as well. So actually, this kind of movement happening in blockchain space as well. So I think you are familiar with the modular approach, that there are settlement layer, DA, and also execution layer. We call it rollup or layer 2. But we need to achieve more scalability and more cost effectiveness. I think we need to move on from modular to microservice, which means that with rollup approach, there will be many modules than the existing modular architecture, such as there will be builders to extract MEV from a builder, and also executor, which is a stateful node to keep tracking of the latest state for rollups as well. And also for ZK proof, ZK rollup, there will be ZK prover to generate the ZKP to prove the integrity of state transition for these rollups as well. So what kind of modules do we need to coordinate these all modules? We think that sequence layer, especially that Radius is building, is kind of needed to coordinate these whole kinds of modules to achieve scalability, which is the ultimate goal of rollups and true Ethereum as well. So I know you guys are familiar with the rollups, but I just go over the benefits and some problems that rollups and true Ethereum has right now. First of all, rollup is just a batch transactions from user side offline, and then make it a one bundle transactions. So and then submit to Ethereum. So which means that we can achieve a cheaper transaction fee compared to Ethereum, because many transitions into one transition for Ethereum, so it's going to be really cheaper, and especially with EIP 4844, it even more cheaper transaction fee with this block transactions as well. Also, rollups is kind of inherited security from Ethereum, so there should be no worries about this security. So these rollups can provide much more faster pre-confirmation, which means that users don't need to wait like 12 seconds or even 15 minutes, which is the finality time on Ethereum. So this fast pre-confirmation thing leads to better UX for user side. Also, the reason why recently rollup is kind of chosen to deploy these dApp services compared to a smart contract, because these development environment is becoming mature. Like rollup frameworks, many rollup frameworks are open sourced, like Madara from Starkware, Starknet Tech Stack, or OP Stack from Optimism, and ZK Stack from ZK Sync. They are really right now. It's kind of ready to use to deploy your own rollups as well. And also there are many rollup as a service providers, just such as Outlayer, Caldera, and many others that you can just with one click you can deploy your own rollups as well. So I think there will be many rollups in the future, I suppose. But the problem is that the existing layer 2s right now running on centralized sequences, which means that if they want to, they can censor your transactions, they can extract harmful MEV, such as front-running and sandwich attack from you guys. And also, there will be single point of failure that you can, I think you've experienced sometimes that they just stop working. So that's why they have some kind of a decentralization of sequences on their roadmap as well. And another big problem is that a liquidity fragmentation, which means there's no way to communicate each other with multiple rollups. So liquidation, there's no good way to support this interoperability between multiple rollups. So users experienced really bad UX because your assets kind of are split into different rollups as well. But there's some kind of a solution for this liquidity fragmentation, such as bridge. But if you witnessed that there's some kind of a really big hacking happened with bridge. So it's not like not safe way to support this interoperability between rollups. So these bridges just support this asynchronous composability for multiple domains or multiple rollups, which means that if you want to move assets on rollup A to rollup B, it takes so much time to get finalized. So yeah, so that's why shared sequence layer concepts came out. Especially shared sequence layer can support synchronous composability for multiple rollups, which means that synchronous means that you don't need to wait base layer, such as Ethereum, to finalize your transitions, so you can get much better experience when you want to move your assets between multiple rollups as well. Which means a single sequencer monopolies the rights of building blocks for multiple rollups. So this sequencer can do whatever they want. So if, for example, on the diagram, a user wants to do some kind of a flash loan transactions, a sequencer can guarantee that these transactions in flash loans transactions are going to be included in a targeted rollups, each rollups, such as one transitions in rollup A, and another one would be included in blocks for rollup B. So this can guarantee the atomicity for transitions in bundles. So that's why we call this sequencer a shared sequencer. But the problem is that I think you can notice that some kind of a monopoly is kind of really bad words, especially in blockchain space, which means that they're going to be really single, highly centralized sequencers if we want to support this synchronous composability for many rollups. So there should be some way to mitigate the power of decentralized sequences. And then Radius has got our own way. I will explain later. And then another one is that these centralized sequences only guarantee the atomic inclusion, actually, which means that because sequencers have the right to build a block, it's easy to include those transitions from Flash-Learn into each blocks for each rollups. But the problem is that this sequencer cannot guarantee these blocks that he proposed actually executed or not. So we need some kind of additional mechanism to guarantee this atomic execution as well. So I will explain later. So Radius that I just founded 2 years ago, we are doing this sequencers on-demand service. And then also we are building composability solutions for rollups. And then the way to provide our solution is kind of a client-centric approach, which means that we've been discussing it with the multiple rollups or multiple dApps who want to deploy their own rollups. We'd like to help them to deploy their own rollups kind of an easy way, and also make sure that their sequencers are kind of running their sequencers in economically sustainable ways. So, and then our solution is kind of layer agnostic. So we can support app-specific rollups and also general purpose rollups, such as the existing layer 2s. So I will explain details for each topics. First, sequences on demand service, which means that first of all, there is a needs from roller space that they need to decentralize sequences. Actually, this rollup approach, you don't need to have decentralized sequences because it's kind of off-chain solution. So if you want to maximize the scalability for rollups, you can have a centralized one, and then security can be guaranteed in Ethereum. So there's nothing much these centralized sequences can do, but some kind of censorship and also MEV is kind of the way these centralized sequences can do. So it leads to financial losses on user side. So there's some kind of requirements from these rollup side that they need some kind of concrete mechanism to provide this censorship and MEV resistance. And then also, aliveness is really matters because centralized sequences can stop working anytime. So which means that it will lead to bad experience for user side. So our sequencers on demand service will provide this censorship and MEV resistance and also liveness guarantees for these rollups. How we do that? We implemented our encrypted mempool, which means that when user creates transitions, they need to encrypt transitions. So when sequencer build a block, they cannot see the contents of transitions, which means that they cannot censor or they cannot extract bad MEV from these transactions because they cannot see the contents there. So so that's how we prevent this censorship and MAV happening on sequencing side. And then another one is the liveness, that we our shared sequencing layer is working on based on leader-based sequencing, which means that we don't have consensus mechanism when building a block. Because we use an encrypted mempool, there's nothing that this leader can do, such as like a manipulate order or something. So that's why we can just leader-based sequencing compared to consensus model. So which means we can guarantee the maximized the scalability for rollups. Another one is that based sequencing things. It's kind of new one. I hope you've heard of it, but usually like a layer 2s, the existing layer 2s have their own sequencers, but the problem that when we wanna like a composability between two rollups, there's some way to have some kind of economic alignment between layer 2s and also layer 1 as well. So we cannot ignore this layer 1 ecosystem, because layer 1, when layer 2s wanna finality on their block, this layer 1 validator should include these transitions from layer 2 in their blocks as well. Which means that if there is no economic alignment between layer 2s and layer 1, layer 1 proposals easily ignore transitions from layer 2s. So that's why this based sequencing concept is proposed from Ethereum Foundation, that layer 1 proposal has both the rights of building both blocks for layer 1 and also layer 2s. So so we can have some kind of synchronous composability between layer 1 and also layer 2s. And then there will be no worries that these layer 1 proposal just ignore these layer 2's blocks. So this is kind of really a big value market. That imagine if we can build these flash loans between happening between layer 1 and layer 2, there will be many use cases and then many profits that can make, especially maybe builders or proposers. So this is basic sequencing is the way to achieve composability between layer 1 and layer 2, so that we are going that way. Okay, so another one is that right now these centralized sequencers for existing rollups are generating a massive amount of profits with running their own sequencers by themselves. How can they do that? They just collect transaction fees from user side, and then they somehow overcharge the transaction fees on user side, and then right now they are making a huge amount of profits. So there is no reason for them to give up these profits. It's all about the economics. So if we want to enforce these layer 2s to obtain shared sequencing layer, there should be some way to guarantee some amount of profits for these rollups as well. And also this shared sequencing layer needs to generate profits for themselves. So how we can do that? First of all, radius approach. We are gonna support this native token neutrality, which means any entity who wants to become sequencers for our shared sequencing layer, they can stake their their layer 2's native tokens, which means that before with this based sequencing thing, layer 1 proposer is going to have all the rights to build a block for these layer 1 and layer 2s, which means there's no utility for layer 2 tokens. But with our design, we are going to support this native token staking as well. And then another one is that it's really important for rollups to generate enough profit so they can run their network economically sustainable way. So that's why we adopt these MEV auctions when they build a block for layer 2s. Usually right now the existing layer 2s have ordering policies of first come first serve, but with our design we split block space into 2 parts. Top block will be assigned to MEV searchers, so any entity who can extract a benign MEV, not a harmful MEV, can make a bundle, and then they can join the MEV auction, and then they can make a profit from this top block space. And then bottom part of this block will include transactions from this encrypted mempool, so we can protect user side from harmful MEV and censorship attack. So these, so the revenue or these profits made from this top block will go directly to rollup space or rollups, so they can keep their network sustainable in economical way. So I'm gonna deep dive more with the technical thing. So I will explain our encrypted mempool, how it works, and then probably another one, something more. Yeah. Anyway, encrypted mempool, there is a couple of ways to implement encrypted mempool. One is that probably the common way to implement encrypted mempool would be based on threshold encryption, which means that when you generate your transactions and then encrypt your transactions, you need to split your encryption key and then deliver it to third-party key holding parties. So when sequencer needs to decrypt transactions, they need somehow collect some part of these decryption keys, and then they can decrypt, which means that they need to trust or depend on these third parties, key holding party. But we don't want to like a additional trust assumption. That's why we went for delay encryption, which means that it's based on time lock puzzle. So when user creates transactions and when they want to protect their transactions from sequences, they generate a time lock puzzle, and then the solution to time lock puzzle will be used as an encryption key. So when they encrypt, and so after user submits this encrypted transactions and time lock puzzle to sequencing side, sequencer needs to solve this time lock puzzle to find a decryption key. So this delay can happen from this when sequencers solving time lock puzzle. So during this delay, sequencers need to respond to user with some kind of order commitment, saying that I cannot see your transactions, but I will make sure that your transactions will be included in a specific index of next block. So it works like a fully trustless sequencing way, but the problem is that there is a kind of computational overhead on user side, because they need to generate time lock puzzle, and also to prove the integrity of this time lock puzzle, they also need to generate ZKP for that. So some kind of trade-off in that. So we recently came up with our version 2 of our delay encryption, which is the single key delay encryption. So in that case, a set of sequencers are are responsible in generating the single encryption key for per epoch. So with this single key delay encryption, you just don't need to generate their encryption key anymore. So also, which means that there will be no latency on user side. So it's gonna be the better user experience for them. So how can we do that? A committee of sequencers are selected randomly, and then they are gonna generate single key based on homomorphic time lock puzzle. So and then also they need to generate a ZKP that to prove the integrity of generating encryption key as well. So with verifying the proof, a user can make sure this encryption key is kind of legit. So yeah. And then other one is that as I said before, these sequencers, especially leader, need to issue this order commitment to user side when a user submit transitions. And then after these leaders post the next block to Ethereum, user can easily find out this order commitment is kept or broken. It's broken, user can claim, and then this malicious leader is going to be slashed. So that's why we are right now collaborating with the eigenlayer. So this slashing mechanism can be adopted quite easily with the restaking protocol. Okay. So another one is that it's synchronous composability. That usually shared sequencing layer is kind of stateless, which means that the sequencers for this shared sequence layer don't keep the states for each blocks, which means these sequencers cannot execute transactions because they don't have any states. So I think that it's kind of intention to support multiple rollups at the same time. But to support synchronous composability, there must be some level of executions for each rollups. So that's why we came up with this atomicity protocol that when user submits some kind of flash loan transactions to sequencing side, sequencer guarantee atomic inclusion quite easily, and then also they are gonna guarantee atomic executions by executing these transitions in the flash loan transitions. How can we do that? We wanna keep this shared sequencer stateless, so these shared sequencers just delegate the execution of these transactions for each rollup to executors. It's full load for these rollups. So I will just post this link to our architecture on Ethereum research, so you can read that. So yeah, with this mechanism, we can guarantee atomic execution quite efficiently, I suppose. I mean, if we want to support like a full level of composability with all rollups, it's really impractical because executions of these all rollups is kind of really computational overhead. So as I mentioned before, actually not all rollups wants to communicate with all rollups. They just want to communicate with the rollups that they choose to communicate each other. We call it a clustering clustering sequencing thing. So this kind of approach can this composability mechanism kind of practical because there's a limited number of rollups to communicate each other. Another last one would be low finality cost, which means that Radius came from this ZK community, so we want to solve many problems with this ZK, and then we also need some way to reduce operational costs for rollups So the easiest way to reduce this operational cost would be with the proof aggregation, which means that posting this ZK proof and verifying this proof on Ethereum is really expensive. So we just aggregate multiple proofs and then make one, so we can reduce easily this cost. And the other one is that we make sure this sequencer can find the cheapest way to generate the ZKP, which means that we are building some kind of a competitive ZK proof auction thing with multiple ZK proof of market. So if rollups wanna find out the cheapest way to generate ZKP, we can start proof auction. So we can ask these multiple ZK proof of network with like maximum due or budgets that this sequencer can provide. So they can bid, and then the operational cost will be reduced as well. And then also, obviously, sequencer can have some kind of dedicated ZK proof market if they want as well. So that's all of my talk. Thank you so much.